Hi everyone, my name is Nour Fahmy and I am the Math and Foundation stream owner here at ACE. ACE, if you've never heard of us, is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the other live sessions and other free content we publish. We currently have more than 30 different streams that are focused on various ML topics, and this session is in Math and Foundations. Hope you enjoyed and come back. Today we have Dr. Niall Jeffrey from École Normale Supérieure in Paris. And without further ado, please start us off.
Okay. So hello everybody. I'd like to talk to you today about this mouthful of a title that I've written down, but I suppose I can break it down somewhat. So the main takeaway is high dimensional parameter inference. I'll talk about 2 different methods of marginal posterior densities and moment networks, but then really I'll talk a lot about applications to the universe, so the field of cosmology. So myself, I'm a statistical cosmologist, and I work in Paris at the École Normale Supérieure. So a lot of the problems we're solving are motivated by cosmology, and I'll talk about that mainly, but also the work here is very applicable to lots of other areas of data science, machine learning, and statistics as well. But my route into this has been through studying the universe. So the outline of the talk will be, I'll start off talking about those kind of motivations, in particular, the problems of high dimensionality in the physical problems that we're dealing with. I will then go through the 2 methods I was going to talk about, so marginal flows and moment networks, so how we deal with these problems. And then I'll end with 2 interesting applications here. So one is gravitational waves, waves in space-time that one can detect. And the final one is the oldest light in the universe, the cosmic microwave background. So I'll talk about some applications to that as well. So the motivation of the physical problems that lead us to these kind of questions. Again, there are many applications, not just in physics, but these are the ones that got me into it. So one is the cosmic microwave background. And so we're talking about high dimensional problems here. This is the thing we're trying to solve. So it's sometimes known as the oldest light in the universe. And this is an image across the full sky. One can think of it as a world map, but looking outwards at the microwave sky. And this is temperature fluctuations in that light, if you could see it. And this is extremely high dimensional, this problem. So in such a map, one could get up to 1 billion pixels across the night sky. So extremely high numbers of pixels. And if each pixel is itself a parameter, then you have a parameter space, which is dimension 1 billion. So it becomes very large and very kind of intractable if you do naive methods that you want to solve these kind of problems. And we use the cosmic microwave background to teach us about the Big Bang, because it is the oldest light in the universe. Another kind of high dimensional problem that we have in cosmology is the growth of structures in the universe. So sometimes known as the cosmic web. So we try and observe this and then use how the cosmic web looks across cosmic time to infer models of the universe. So here you can see the start of a simulation of the universe, of a patch of the universe, and it's a box that you can see through here. And as I set the simulation going, the box, you can imagine expanding. It won't expand, but I've fixed it in place, but it will imagine it expanding and expanding. So we start off with this Gaussian random field in the early universe. So we have these Gaussian fluctuations. And now as it evolves, the Gaussian fluctuations lead to collapse through gravity. So any over dense regions start attracting more matter onto it. And then you end up, as the simulation evolves, with this rich cosmic web structure. And again, this kind of data, observing the cosmic web over cosmic time, is extremely high dimensional if one thinks of every point in space as a parameter to be inferred. So we might want to know the density of dark matter in a given point in space. And this might be dependent on all sorts of other points in space as well. So in many problems, we want to infer either cosmological parameters or the actual cosmic web itself. So we usually set up a parameter inference problem, not just in cosmology, in many areas of inference, or in particular physics. So we have some observed data, and here data can mean any summary statistic of one observations. And let's call it X O for observation. So that's our observed data. And it's straightforwardly, we want to target the posterior distribution. So the probability of our parameters, theta. So these theta parameters could just be simply a few values that describe the universe, or they could be every pixel in that cosmic microwave background image you saw. So we want to know the density, or the probability density, of the parameters given our observed data. And this is proportional to the likelihood term, or factor in this case, which is the probability of that we observed our given data given the parameters, and then a prior term. And if, for example, in many problems we either don't know the prior, a priori, as it were, or analytically, and we don't know the likelihood, or more specifically, we don't know the general sampling distribution. So the distribution P of X, P for X given theta, where X is any value of the summary statistic, not just the one we observe. So in many problems, we want to do something that's often known as likelihood-free inference, where we try and estimate this sampling distribution from our simulations. And a popular method at the moment, both in many different fields, is density estimation, likelihood-free inference. So the problem set up is that we have our sampling distribution, the probability of X given theta, our parameters, and we don't know what P of X given theta is analytically. We can't write it down in closed form, but we might be able to draw training data from that distribution. So we don't know what P is, but we can draw realizations of mock data X from that distribution. For example, by running a simulation where the data X contain all of the noise and observational effects that one would get from from the actual data with a real world instrument. So we have these simulated data vectors X, and we have associated vectors of parameters theta. And we want to reconstruct what the conditional density P of X given theta is. So for just a one-dimensional example here, you can think of one parameter theta and one parameter X, and these samples X and theta form each dot here, so they form a cloud of points. So if theta itself is drawn from the prior that we want to use in our inference, then these points, this cloud of points, are drawn from the density P of X and theta. But even if theta is not drawn from that prior distribution, then from this cloud of points, one could, for example, estimate directly the conditional distribution P of X given theta. So that's the aim here. So we want to estimate these densities from the simulations that fill up our parameter and data space. So I won't go into the details of different neural density estimation methods, because there are many varied ones and it's a very fast-moving field. But the main aim is that we have our training data X or Xi and their associated parameter labels theta I, and we want to construct some estimate Q of the density from which those realization or those samples were drawn. So we want to use a neural network or any kind of method, but a neural network to estimate this Q, and we want it to be as close as possible to the underlying P that we don't know analytically. Because once we've evaluated this density Q of X given theta, then we can evaluate it for our actual observations of, for example, the universe, and then get ourselves our likelihood. And typically this is done by parameterizing Q with a neural network with parameters phi here. And what one does is one minimizes the logarithm of Q, or the negative logarithm of Q, evaluated for all the training data. And what this in practice does is finds Q that best fits the conditional P of X given theta. So we, through training of a neural network, we're able to get this estimate Q. Okay, so the problem that I started off talking about was what happens when you have very high dimensions. So if you have a very high dimensional data set, but a very small parameter set, then the problem is most simply overcome by just compressing the data down to a smaller set of data points. So for example, if one wanted to infer two parameters that describe a system, then, but one had a very large data vector with, for example, thousands or millions of elements in, one typically, for many problems, can compress that data vector down to only two or a few greater than that. So we can do a large data compression, and that removes the high dimensionality of the problem. But what happens when the parameters are themselves high dimensional? So what happens when we have a billion parameters? We can't, compressing the data won't help us here. And you might think this is not a very big problem, maybe. Well, it's only, for example, a billion parameters. You can plot the image I showed before of the cosmic microwave background, but actually it scales very badly when you go to high dimensions. So it's actually the probability distribution, or the probability density, that ends up having a very high dimension as well. And just a typical kind of cartoon example to see how this scales is that if you have 5 samples to define one dimension, then you need 25 samples to define 2 dimensions, 125 once you get to 3 dimensions, and this scales very, very badly. So once you get to a billion dimensions, there's no way you can do it. You can calculate it. You would need a computer with more CPUs and atoms in the universe for some of these problems if you were just to evaluate by brute force this full dimensional problem. So this is where the marginal posterior density comes in particular marginal flows that I'll talk about. So for many problems, imagine you have this very high dimensional problem, like you have the pixels of an image where each pixel is its own parameter. Then we say, well, we can't tractably find the posterior distribution for the full set of pixels. But what we can do is that we can target just the posterior, marginal posterior. So we marginalize over all other parameters, for example, 2 pixels. So we have alpha and beta, and we might just want to target the equation at the bottom here, which is just the marginal posterior distribution for alpha and beta, given our observed data, where we have marginalized away the other parameters, meaning we've correctly taken into account our uncertainty in those parameters as well. But typically, if you do this integral, this again involves the integral over this very high dimensional density you have on the right-hand side. But I should say that in practice, the very high dimensional probability density is typically not needed. So I'll just give an example again from cosmology, but you could think of it in image analysis as well, where actually here you have 3 parameters that describe a cosmological data set. W is describes dark energy, the omega describes the amount of dark matter, and M describes a property of supernova here. So this is a straightforward problem, but typically one just represents the marginals for pairs of parameters. And this typically gives us the information we want to know about how the parameters are correlated, their covariance, and so on. And one can think in an image that one might want the posterior mean of a pixel, the posterior, and then the marginal posterior per pixel, and then the marginal joint marginals between all pairs of pixels. And then one could do something similar to here, where one has characterized all of the correlations in the posterior distribution of one's recovered image. So one can set this up as a masked autoregressive flow or a normalizing flow to estimate Q, where Q is the target. But it doesn't need to be a normalizing flow. We just need a neural network that estimates this density. So we're trying to just target pairs of parameters in this huge, highly dimensional parameter space. So the first step is that we draw our realizations for our training data. We draw our theta parameter from the prior distribution. So in the case of images, this means drawing the full image from the prior distribution of possible images. We then do the second step again, where we generate mock realizations of our observed data, conditional on that previous draw from the prior. So we might add noise to our image, for example. And now the objective that our neural density estimate minimizes or tries to optimize is now not the estimate for Q of the data given the full set of parameters. We've now flipped it and removed all parameters but two. So it's now the Q of our two parameters, alpha and beta, given the full data set. Now, this may seem like we've lost all the information about the other parameters, but actually, as long as one follows this procedure and draws all the parameters from the prior, but then only does the kind of likelihood-free inference step on those pairs of parameters, then one has formally marginalized away all of those other parameters correctly and correctly taken into account our uncertainty in all those other parameters. So we've robustly got the thing we care about, which is the posterior distribution for what we want to know, which in this case is the parameters and pairs of parameters. Okay, so with this technique, or with this setup, we're able to solve very high dimensional problems that otherwise one would not be able to solve with the optimization I showed before. And one can compare it with Markov chain Monte Carlo. So here we have a 100-dimensional parameter problem. So we have 100 dimensions, 100 parameters, but we say we know the likelihood just for comparison. So we know the statistical model, and we're able to sample from it using Markov chain Monte Carlo. And using 10 to the power 7 MCMC samples, you can get the marginal distribution you can see on the right, the marginal posterior. But with only 8 times 10 to the 4 data realizations for the marginal flow, we're able to also constrain these parameters and the posterior distribution for these parameters, as well as the MCMC, but we've never had to go to the full 100-dimensional problem. Whereas with the MCMC, the marginalization, we have to sample all of those parameters. Whereas here we've targeted directly just the thing we care about. Okay, so the second methods element of this I wanted to talk about is moment networks. So the idea here is that for many problems, again, we don't actually care about the posterior density or the posterior distribution for each parameter. For many problems in physical sciences, but also in just any kind of data analysis, the underlying signal or parameter space, we don't need the full posterior distribution. We might just want, for example, the mean of the posterior, variance or standard deviation of the posterior, and then also the correlation between all parameters, so the covariance of the posterior distribution as well. So this is what a moment network does. We try and estimate those moments of the marginal posterior rather than the actual marginal posterior themselves. And it's therefore far simpler, far more, it requires far simpler networks, and therefore there's less risk of something going wrong. So we just have a simple regression network, but we train it in this hierarchy so we get these moments. So the first network is this F function, and it takes in the data as an input. And this F function is trained just using an L2, so mean square error loss. So overall, this training procedure minimizes J0 here. So the first factor is will just be the loss during training, where you have the true values of the parameters theta or signal, which is high dimensional, and F is your neural network to be trained. But again, just a simple regression network. And if we minimize this mean square error loss, where we've drawn the parameters from their prior, and we've drawn the mock data from that sampling distribution with all the correct noise properties, then formally then the optimal network is, when evaluated for the actual observed data, ends up being the posterior mean. So this isn't a new result, it goes back a very long time, but it means that we're able to do the first step, which is without estimating the marginal distributions directly, we've just directly gone for the posterior mean. So then we have the second step, so the second level. So in the hierarchy, we have our mean, and then we want to get the variance or covariance. So we have G as our second layer of this network, where the optimization objective ends up minimizing this J1, where the first factor in the integral here is, again, an L2 minimization, but you end up with theta parameters, subtract the fixed network from the previous layer, which gives you your mean of your posterior. You then square that, and then your network tries to output that object under a mean square error loss. And then again, as long as you've drawn theta from the prior and x from the sampling distribution, then this G network will give you the variance, the marginal variance per parameter when once it's trained optimally. And again, you can edit this slightly to get all the covariance of your marginal posterior distribution as well, and also go to higher moments of the marginal. Okay, so again, I just do the comparison I did before, where on the left was the result from before the marginal flow, and on the right is a result for the moment network. Again, the Markov chain Monte Carlo knew the likelihood, but sampled in the full 100-dimensional space before marginalization, whereas the moment network, bam, straight out of the box, it gives you the mean, variance, and covariance between pairs of parameters. So you can construct the parameter correlations in the marginal posterior for all of your pixels in an image, for example, and quantify that uncertainty. Okay, so now I'll talk about some applications. So in this case, gravitational waves. And in particular, merging black holes is the example I'll talk about. So this is an artist's impression of two merging black holes, where you have the black hole in the center, and then the bright bit around the outside is the accretion disk. So it's matter falling into the black hole. Whereas what we're going to focus on is black holes orbiting, and then they emit energy through gravitational waves, and then they merge. And just here's an animation of two objects orbiting, and you can see these ripples in this space-time animation. And sometimes gravitational waves are called ripples in a space-time pond. So we on Earth, very distant from these orbiting bodies, can detect these ripples in space-time using laser interferometers, which are two lasers set at 90 degrees from one another, so they can detect these subtle distortions. But bringing it back to the example of high dimensional parameter inference, what's the problem here? So the gravitational wave data, so on the left example, for example, to take first, you have the orange dash line, and this orange dash line is the raw signal that one should detect in an optimal detector. But in fact, you have all this noise and stuff which makes it more difficult to see the underlying signal. And in this example, each time step of the signal is itself a parameter. So the posterior distribution for your signal can be over 100-dimensional in this example. So just to show you, to explain the difference between these two plots here, the left is the example where the black holes are just orbiting one another, so they're giving a relatively clean sinusoidal signal. And on the right, you have emerging black holes, so they end up with an increasing amplitude and frequency until they merge at the end. So the problem is we want to infer these underlying signals, which have a parameter for each time step, so it is very high dimensional. So here's the example with the moment network. So the orange dots are the data, the green solid line is the true signal, and the blue contour is the 1 sigma, 1 standard deviation marginal posterior for each of these time steps, which we're able to do with the moment network. So we're able to solve these very high dimensional problems that, using the setup I described at the very beginning, this would be intractable. But using the moment network, or alternatively just estimating the marginal posterior densities, one is able to do this very quickly and very robustly. And we can see that on the right here, where we have an analytic example where we know the likelihood. And you can see this with the green dash line. And then the moment network is the orange contours, where you can see it matches the known result from MCMC very, very well. So it's also statistically robust as well. So using this, we're able to detect orbiting and merging black holes in the presence of very high levels of noise. Okay, so my final application is talking about the cosmic microwave background, so the CMB, in particular the problem of foreground, so things getting in the way of your CMB image. So the scientific motivation for this is the search for something called B modes, which are a signal in the CMB. So the cosmic microwave background is microwave light, but in addition to an intensity, so that was the image you saw right at the start of the presentation, in addition to an intensity, it also has a polarization. So it has a polarization angle as well. It's linearly polarized as well. And here you can see an image from the Planck satellite of the microwave sky. And we're searching for a particular pattern called a B mode, which is a direct signal of something called cosmic inflation, which will tell us new physics about how the Big Bang happened. But the problem is that what you're seeing here is not primordial B modes from the early universe. The image here is almost entirely swamped by microwave polarized emission from within our own galaxy. So the big line you can see across there is our own Milky Way, which is emitting a huge amount of polarized microwave. So the problem is trying to remove this foreground stuff so you can get to the primordial signal and then detect these signals of the Big Bang. So we'll use a moment network as in this example. So again, our network takes the data as input. We have a hierarchy of networks, so we can get the mean of the posterior, a marginal posterior per pixel. We can get the variance of the marginal posterior per pixel, and we can also get all the covariance terms as well. And if we get this, and if we learn these properties of the posterior probability density of the primordial cosmic microwave background, then we're able to discover new physics of cosmic inflation. So these are some of the examples. So we're able to draw realizations of mock foregrounds, where here you can see typical images where the signal is entirely swamped by foreground emission. These images don't use the polarization because it's difficult to plot, so I'm just showing the intensity of the signal, but the same steps would apply. So with these noisy and foreground dominated images that are masked by our own galaxy, we want to see the primordial cosmic microwave background. So before I do the final showing of our result with the moment network, I just want to show you what the equivalent would be with current typical methods. So this is slightly simplified, but it's a direct, fair comparison with what the current methods would do. So rather than using moment networks or high dimensional likelihood free inference, we have a Bayesian hierarchical model with a Gaussian distribution. And we solve it in a kind of typical way. So here's our foreground observed data. And then with our model, we can infer the primordial signal. And unfortunately, you can see at various points, for example, here and here, you end up with a residual from the foreground in our signal. which is no good at all. It means that we haven't actually been able to properly clean away this foreground signal. And what's more with this procedure, if we have our uncertainty in our image per pixel, with this hierarchical Gaussian model, our uncertainty or our variance of our marginal posterior per pixel is constant everywhere. So it doesn't take into account the fact that in certain areas we expect more uncertainty because there's more foregrounds. So we would expect that to be reflected in the uncertainty per pixel. So now the result with the moment network. So we're inferring the CMB image where the problem is high dimensional because it has as many dimensions as the number of pixels. So this is our input once we've trained out. So we train this method, and then this is the result. So this is the foreground obscured data. And this is the result with the moment network. So the moment network is being able to get the marginal posterior per pixel. So this is the first layer. So we get the marginal posterior distribution per pixel. But importantly, what we can also get is the next layer, which is the uncertainty quantification. So we're able to get the variance of the marginal posterior per pixel. And we could also get the covariance between all of the pixels as well. I just can't plot that easily here. But using this method, we're able to properly solve and take into account uncertainty in this very high dimensional problem. And you can see that the uncertainty is accurately reflecting the uncertainty we should have, which is in some places our image has got more astrophysical foreground blocking the primordial signal. And you can see that that's reflected in the high variance points in the moment network output, which one can compare to the data. And using this, that we will then be able to go on further and detect these primordial B modes in the cosmic microwave background. So this signal, which will then tell us new physics about how the Big Bang happened. So with that, I'll end. Thank you.
Wasn't that quite interesting, audience? We've got quite a few questions for you, Niall, if you're ready.
Yeah, sure.
Perfect. So the first one is from Amir Faispour, and he's asking, what are we giving up by using the simulation instead of the full MCMC?
Well, one doesn't need to give anything up, really. Whenever one has MCMC, one knows the likelihood. So this whole procedure also works if one is able to sample data from that likelihood as well. So you can also use these methods to jump over MCMC and just directly get to the posterior distributions you care about, if you do have that likelihood and you can sample realizations of the data. But also in this case, we don't actually need that likelihood. So we can, for many problems, we can do better even when we have a likelihood, but also we can solve problems that we wouldn't be able to otherwise.
Perfect. I'll wait for Amir to follow up if need be. We have a second question from Neil Bartlett, and he's asking, are the covariance matrices denoised using random matrix theory?
The covariance of the if the question is related to the covariance of the posterior, then no. There's no denoise. Maybe I've misunderstood, but the covariance is the covariance of the posterior distribution directly. So no denoising takes place. We directly target what the correct posterior distribution would be.
Awesome. And Neil has also just clarified that it was the posterior distribution that he was referring to. We have another question from the audience, and it's asking, if we don't have the prior or the likelihood, what's abstaining us from using a frequentist approach?
Well, this is the whole Bayesian debate.
Yeah.
Look, my view is you always have a prior, and then you can choose to be explicit about that or not. In any machine learning context, there always has to be, there are prior distributions and prior assumptions that are going on. So if you have a set of training data, usually one can think of that as a prior. So I would say that you always have a prior. Maybe you can't write it down analytically, and that is many of the problems here. that you could, for example, sample from the prior, but you can't write it down in closed form. But I would say for most problems, you do have a prior, and if you have training data and you think it's not from a prior, you might need to rethink what's going on exactly there.
Excellent explanation. Another question we have from the audience is, how do you choose which two parameters to use for marginal flow? Does it depend on the context?
Well, typically the idea is to use all pairs of parameters. So I know that might seem like a lot, but so imagine I have 100 parameters, for example. So that scales to the power of the dimension. Whereas if I just do all pairs of parameters, it just scales as squared, basically. So it's combinatorically, it's much simpler. So one can just do all pairs of parameters.
Awesome. I believe that is all the questions from the audience. So with that, I'd like to thank you, Dr. Jeffrey, for joining us today. And I'd like to thank you, the audience, for joining us today as well. And to see more free content like this, visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. Thanks, guys. And then Xiang will log us off.
Okay.